Hello everyone and welcome to our Senior Design Project Review. Our team is SP21-3, but you can call us Digital Guide Dog. Our team consists of 3 computer engineers, Griffin, Bradley, Anthony, and 2 electrical engineers, Harry and Karen. The goal of our project is to create a cane attachment that performs object avoidance and detection to guide those who have vision impairments. The attachment should easily fit onto an existing white cane, give the user vibration motor feedback, allowing them to know how close they are to an object, perform object detection to detect medium to large household objects, such as chairs, couches, and tables, as well as know the object's distance and direction. All of this information will be relayed back to the user through a text-to-speech program. The motivation for our project stems from the fact that only about 8% of people with vision impairments use a white cane, while the rest choose some other form of guiding assistance, such as a guide dog. This is most likely due to the limitations of the standard white cane shown on the screen now. Typically, it is only used for avoiding obstacles within its limited range, which is about 1.5 meters away. There is no way to detect what the objects are, where the objects are, or guide the user in any way. We hope to change that. Initially, our handle design was created in AutoCAD. At the top is the base of the handle. The base contains grooves, easily allowing the user to grip the handle. These grooves also serve to store the vibration motors, which notifies the user when they are approaching an object. There are holes at the top of the base to store push buttons. These buttons allow the user to interact with the handle and the underlying code. A white cane can easily slide into the base of the handle, then be tightened down to secure it. In the center of the handle is a platform which holds the Raspberry Pi and the prototype board. The end of the long shaft holds the depth camera. This places it in proper position to efficiently detect objects. And this is what the project looks like with everything 3D printed and attached.
All right, this will be an overview of the overall product. And on the bottom left, you can see the transistors to control the motors, as well as 3 wires to control them, powered by the AA batteries up top. And then on the top right, there's the wires for the buttons. And it's all connected to the Raspberry Pi, which is the black metal case behind it. Then up top, you can see the depth camera, the D415 Intel RealSense camera. Then down here, you can see the 4 buttons that are embedded into the device for user input. And then the 3 motors go into these little cylindrical slots with some cotton to dampen the noise and vibration. And now this is how you typically hold it, with the depth camera facing forward to detect obstacles in front of you.
Our hardware components include a Raspberry Pi 4 Model B board with 4 GB of RAM, an Intel RealSense depth camera, 3 vibration motors, and a push button. The Raspberry Pi acts as our main compute resource, which handles all of the processing of image and depth information provided by the camera. The vibration motors are used to provide depth information feedback to the user based on the distance to closest objects. The push button allows for a user to determine whether they would like a list of nearby objects to be shared with them or not. The hardware design is structured as follows. Each of the vibration motors are connected between an NPN transistor, which is in turn connected to the GPIO pins on the Raspberry Pi board, and the ground pin. The collector is connected to a 5-volt battery pack consisting of 2 AA batteries, such that when the GPIO pins output a logic high corresponding to a nearby obstacle, the motors turn on and notify the user. As a safety measure, each motor is connected in parallel with a diode in order to prevent damage to other components of the hardware. The push button is placed such that when it's pressed, a logic high is registered on its corresponding GPIO pin, and the software can process the interrupt that it generates. All electronics in the Raspberry Pi are stored in the product housing. The housing was 3D printed from ABS plastic filament, which is robust enough to provide a solid enclosure that is manageable to handle and easily attaches to commonly sized white canes.
Because our project was more software-based, there were a lot of software packages needed. The major ones are listed below in this table. Originally, our main workflow language was in C++ because it interfaces with hardware input-output the easiest and is typically a good language choice for embedded projects. The problem we ran into with C++ is that most machine learning workflows are written in Python, and it became very complicated working in two languages. At first, we attempted to convert the object inference script into C++ using TensorFlow's C++ interpreter, but after many package and import errors, we went a different route. What ended up being our best solution was to interface with the hardware using Python packages and keeping object inference code in Python. TensorFlow Lite was the main machine learning framework we used to load the object detection model and run the inference. Originally, we were using TensorFlow when we worked with the mask-RCNN model, however this proved to be too slow. PyRealSense is the API that is provided by Intel for interfacing with the depth camera. This is where we learn how to get depth information and work with the camera. For example, setting the resolution, frame rate, and other general important features. GTTS is Google's text-to-speech program that provides a smooth voice. This proved to be the best TTS program, however, it does require an internet connection. Lastly, GPIO0 is the main Python library used to interface with the hardware and the Raspberry Pi, namely the push-button and vibration motors. Another major package we used was OpenCV to display the depth camera frames as well as the bounding boxes around the objects detected. However, this is used for testing and debugging purposes only, so the section is commented out for our production. The user will not see an actual picture, therefore it is unnecessary, and leaving this out greatly speeds up the project. Due to the social distancing measures taking place this year, our team had to remotely work on the software for our project. To do this, we used a program called MOBA Xterm to remotely log into the Raspberry Pi. After specifying the Pi's IP address, username, and password, we're able to SSH into the terminal of the Raspberry Pi. Our main code is stored in a repository we call Virtual Cane, and all of our software packages are installed into a virtual environment to keep them separate from other projects. Lastly, our main script to run the program is called virtualcane.py. All of our code is saved using Git's version control software, and the repository is saved on GitHub. This allows us to keep track of all changes, and it makes it very easy to have multiple teammates work on the code. As you can see, our main driver script simply sits in a while loop and constantly gives the user vibration motor feedback. Using the GPIO0 library, we are able to continuously scan for a button press and then proceed to the object detection to give a user valuable information. By far, the largest part of the project was the object detection and analysis. In order for our project to be successful, inference speed was more important than high accuracy. Therefore, most region-based object detection models would not work. This led us to using a single-shot detector called MobileNet SSD. MobileNet only takes one pass through an image, and then classifies objects through a series of convolutional networks. This works by drawing default multi-boxes called anchors, and each of these anchors is given a probability that this box is the object. The anchor with the highest probability is classified as the detected object. Because MobileNet only needs to look at the image one time, this greatly improves the speed compared to the region-based detectors. Here is a video of our implementation of MobileNet. Keep in mind, this video will not be displayed during the final project demonstration because the user has no use for this visual.
Here we have the object detection, which you can see from the bounding boxes, along with the confidence percentage and the distances beneath the bounding box. You can see that the further away, the less accurate it becomes, and the closer it is, the more consistent and accurate it stays. And then you can see it still works with moving objects, and it still picks up the distances. And then at the top, you can see the text that will be read off to the user. So like person is 1.7 meters in center, or to the right, or couch is 1.9 meters into the center.
Lastly, due to the user's visual impairments, it will be hard for them to read off or visualize the objects detected, their direction, and distance. Therefore, we decided to use Google's text-to-speech program to read this information off to the user. Here's an example of what the user will hear if no objects are detected.
No objects found. Try again.
If one object is detected,
The TV is 5.2 meters away and is in the center direction.
And if multiple objects are detected?
The bed is 1.5 meters away and is to the center direction. The person is 2.3 meters away and is to the left direction.
During demonstration, the user will plug earbuds into the Raspberry Pi as they walk. Because of this, the video will not include this TTS voice, but the demonstrator will be speaking out what they hear. On the right side of the screen will be the video of the project being used, and on the left side of the screen will be the Pi terminal. In the Pi terminal, the green text is what is read off to the user. If no objects are found and/or pass our filtering system, the red text is read off to the user.
The chair is in front of me to the left. TV is also further away to the left. The couch was 1.9 meters away.
Thank you so much for watching. We hoped you enjoyed our project review. Although we weren't able to do this in person because of complications with COVID, we really hope that you were able to see just how hard we worked, as well as the fluidity of our project and how much fun we had during the entire semester. We hope that you saw exactly what our project consisted of and that you learned something as well as we did during the duration of the project. Thank you very much again, and we hope you have a great day.